There are many transistor testers on the World Wide Web. They cost between, say, 10 euros and perhaps even 100 euros or dollars anyway. But there's also, say, a very simple way of testing the transistor in a certain way on its dynamic properties. And I'm doing that here with this circuit that I made. My original idea was, let me see whether I can find a difference between a low noise NPN transistor and a normal NPN transistor. I could not find any difference, but of course this is a very primitive way of testing a transistor, and a more elaborated test has to be done. Anyway, this is the schematic, and I think it's interesting enough to show it. You can see that it is a grounded emitter circuit, and we measure the base current here. Here we measure the collector current. Here is the unknown transistor. It is an NPN type. It has to be an NPN type because an NPN transistor has its collector on the positive. And a PNP transistor has its collector on the negative, and it means that with this setup you can only test NPN Bipolar Junction silicon transistors. Anyway, here you set the bias, 22 kilo ohm or 25 kilo ohm. This is a microampere meter, goes to say 0 to 200 microampere or so, and there is the milliampere meter, and that milliampere meter tells you how high the collector current is, given a certain bias and given a certain amplification of the transistor, of course. The amplification factor in general is the relation between the base current and the collector current, so you can compare here 10 microampere here and 100 milliampere here. That ratio tells you something about the amplification factor. But this is also useful to test it on its dynamic properties. So you can send in to that unknown transistor here via a 0.47 microfarad capacitor, 50 volts or so, a signal, and then look on the scope what's happening. Does the transistor really amplify? And here you can set the amplification. That means that you can also see how it amplifies, how good it amplifies. You can see at the scope whether the transistor is overdriven. You can also see the effects of the bias. When the transistor is not properly biased, you will also see distortion. And in more elaborated schematics on the World Wide Web, you also see here the base voltage often. You can also measure here the collector, emitter voltage, but that's not necessary, at least when you want to do such a basic test as this. So let's look. The sine wave generator is connected here. I think it's around 1000 Hertz or so. Don't know that exactly. Well, this is approximately 1000 Hertz. Switch it off. Here is the waveform. You can see it's pure. And let's see what happens when we change the bias here with that 25 kilo ohm potentiometer. Working at the moment on 13 volts, 14 volts. Important to tell that I could not find any difference in noise for voltages between 6 volts and 18 volts. Anyway, so change the bias. Let's see what happens. Of course, on a certain moment it doesn't work okay any longer. But this doesn't have to be a problem when you want to use that transistor for another purpose, not amplifying pure sine waves. So bring the bias completely to zero. Of course the transistor cannot function. And here I turn the bias pot. So you you can see that there is always an ideal bias, and that directly related to the voltage where such a transistor works at its best, and that's visible here. And there's also that direct relation to the value of the potentiometer, of course. It's also related to the base voltage. Anyway, so what can we do more? Now I turn the 1 kilo ohm potentiometer in the emitter lead. Let's see what happens. It sets the amplification. You can directly see. And here we have over amplification, and that means always distortion of the sine wave. I can make it better visible when I drive up the output level of the sine wave generator. Well, there are many complete distortion, etc, etc. But again, this does not have to be a problem when you want, for instance, use this circuit to amplify a square wave, to drive a circuit that at its end, after this transistor or after a Darlington, needs such a type of waveform, say a driver or so. And it also tells you here, when you overdrive it, how the transistor performs in a certain way when it is when there is an application in a switch application. So I go back now to the normal sine wave. Okay. So that's, I think, say the most important things to tell. It works up to 18 volts. When you want to test on higher voltages, change the value of this resistor, say to 5K or so. Change also the value here, or make it also 5K. When you want to test a Darlington, this must be a 470 kilo ohm potentiometer, but anyway, that's a little bit too far. I only want to tell some basics. Tested this transistor. That is the tip 3055. Tested low noise transistors and normal NPN transistors. Also tested a high voltage transistor, and of course for a high voltage transistor, say the biasing must perhaps be in another way. And of course there must be a high voltage when you want to test such a high voltage transistor properly, but anyway, it also showed that it worked nice in this circuit. And of course, when the transistor doesn't function, you don't see that sine wave. Well, perhaps also interesting to show how does such a circuit change, does such a circuit work again when we go to a higher frequency. And that also means that you can search a proper bias for also the higher frequencies. This frequency must be approximately 15 kilocycles. So let's change the bias. Well, that's still not okay. And change the amplification. Well, here it is a little bit okay. Change the sine wave a little bit. But anyway, these are, say, the possibilities of when you use this test circuits. Thanks for watching. And if possible, take profit. Of course you need an oscilloscope, but anyway, that's logical. You are more or less blind in electronics when you don't have an oscilloscope.